I'm Bang Wonjun. I'll talk about another short channel effect. So first, source drain series resistance is in the parasitic resistance in the source and drain. So it'll remain when transistor is on and off. Will be remain source and drain. So here's the example. Source and drain has 1 kilo ohm and 1 kilo ohm. So when transistor is on, channel will be have a 10 ohm, only 10 ohm. So total resistance is series resistance. So 2 kilo ohm, approximately 2 kilo ohm, and when transistor is off it will be 10 milliohm, and source and drain has 1 kilo ohm too. So approximately off state transistor have approximately 10 milliohm. So it will be problem, it will occur the problem about substrate swing will be off when on state transistor have too many resistance. So it'll be like this. this is the parasitic resistance in transistor. So AC is the AC, and the RSP spreading resistance is the neck bottle effect of, so that'll be have resistance, and SH is the source and drains resistance, and this is the contact resistance RC. This is like a Schottky barrier because contact is metal and transistors is source and drain is semiconductor. So semiconductor and metal contact will have Schottky barrier that can be occur the resistance. So LDD, AC is the junction if depletion, have junction depletion, so it will be made a resistance, very many resistance. So we so LDD can ease the resistance, plastic resistance. And this is the contact issue. I'll talk the contact issue. When I said the contact resistance, so that can be have a contact resistance. The transistor will go down, go very down, scale down. So another parasitic resistance like a spreading or AC or SD or like some parasitic resistance can go down, but contact resistance can not easy to scale down the resistance. So another resistance can go down, but contact resistance remain the first resistance. So it will be So contact resistance proportion is grow. So this is the graph of the parasitic resistance. So here can, so NMOS, this is the NMOS. So another parasitic resistance can go down, but contact resistance that go lower, doesn't go lower. This is not easy. So this is the Schottky barrier. So when equilibrium, that can go here. This is the metal and semiconductor, so it can go down and go, but not go here. But when so this is the IV curve of the metal semiconductor contact. So when lower doping, it will be like a diode diode's characteristic. But when high doping, semiconductor and metal can vary ohmic characteristic. So when we heavily dope to source and drain, it can ease the Schottky barrier effect. This is the MOSFET breakdown. It's like the avalanche. So when hot very many electrofield can made a hot carrier, and hot carrier impact to lattice, and it made a electron hole pair. So electron and hole pair can have very hot energy, so that they also impact. So exponential grow of the hole pair, so it can made very many current. So this like that, it's like a avalanche effect, and that can damage to semiconductor. So hot carrier made because of the electric field, and electric field is very high in junction depletion. So it is about the LDD. LDD is the junction boundary electric field depletion. So, and this is the latch up. In the body, in the semiconductor and body can have the parasitic NPN, because NP and N 2N of the source and drain, and P substrate. So NPN, and it can be made latch up structure in the body. So it can made a latching is so when I turn on the semiconductor, and I want to turn off, but no bias in the VG, but because of the latch up structure, so it can't be turned off. It's the latch up. So we is this effect. So locus and STI and DPI. that decoupling of the transistors, so prevent the latch-up effect. Low cost is like this. Is oxide on the between the transistors, and STI is the shallow trench isolation. So etching shallow and put the oxide in there, and DPI is the deep trench, and go and put the oxide, so isolation is very deep. It can because of the technology development. HKMG is the high K metal gate. So scale down the length, cause the scale down cause the lateral electric field very high, and that can be lose the control of the gate electric field. So we have to grow the gates controllability. So we have to grow the COX capacitance of those oxide, and capacitance of the oxide is like this. Permittivity of oxide and thickness of the oxide over the thickness of oxide, simply thickness of the oxide lower, and COX is grow, but it have a limit because of the quantum tunneling. So we cannot do scale down the T oxide very much of the sub nanoscale. So we have to find another way. So here is the so T thickness oxide grow and C oxide to grow. So we have to grow the permittivity of the oxide high, so we do not use the oxide. Not another permittivity higher permittivity material have the another material. So that is the HKMG, high K. So permittivity and the constant of the permittivity K is very high, and is the quantum tunneling and the growth of the capacitance of the oxide, and we cannot use semiconductor in HKMG because of the semiconductor have depletion and depletion capacitance can withdraw the drag down those capacitance, total capacitance. So we use the metal because of the equipotential. Okay, and we can use the SOI, silicon on insulator. So in the bulk wafer, there are punch through and debul and some poor subthreshold swing. So here's the solution. There is the thin box, buried oxide, so box. It'll be very good because subthreshold swing is 2.3 N kBT over Q, and N is 1 plus C depletion over C oxide. So C depletion will in SOI channel is very thin, so it can be fully depleted. If fully depleted channel have if SOI have fully depleted channel and C depletion over COX will be 0 because C body or C depletion is delta Q depletion over delta VG, and Q depletion delta Q depletion is 0 because of the fully depleted. It can have the change, okay? So subthreshold will be better. And there is a FinFET. FinFET is 3D, not of planar transistor. Its source and drain will be gate is like this. So here, side, both side and top of the channel can gate here. So gate coupling will better. So there are some another FET. This is the 3535. So this structure is like this. So gallium arsenide or aluminum gallium arsenide, and like this. They're not dielectric because aluminum gallium arsenide can hard to deposition of the dielectric. So there are no dielectric, and there is Schottky barrier. So quantum well will here. So quantum well is here. So this is the role of dielectric, and here's the channel. So here's the channel. This 3.5's advantage is electron mobility is better than silicon. So special role transistor can be made about this 3.5 transistor. And here's the JFET. JFET is like this. There are no dielectric, but when low bias like this, there is the depletion region, and here's the channel. So it have the channel. So no bias and channel is have the channel. So this transistor is the depletion mode, and when minus bias in here, so more depletion region and no channel in there. And plus bias, there very small, very thin depletion region in FET, JFET, and when here no bias in gate, and gate is in PP, so and VDS in here, so channel will be thinner because of the VDS, like this. And when touch the each depletion region, there will be pinch off. Okay. And this is the MOSFET. MOSFET is the like a 3-5 transistor. So there is no dielectric. So so it's like a quantum. Dielectric is no. So like a JFET or 3-5. So depletion region will be channel on-off switch, and channel and this quantum well is the Schottky barrier, and this is the roll-off dielectric, and this is the FinFET. So this is like a here, like this, and this source and drain is very large surface because of the low contact resistance can lower because of the large surface of the contact, and it can be punched through because of the body depth is very deep. So P plus doping in here, very high doping in here, so and they can prevent the punch through and dibble. Okay, thank you about the listening.